when we're looking at the relationship between frequency and wavelength, folks, it's defined for you. I don't know. Probably you won't see this on your Regents exam, but just in case, I want to give you the tools and the exposure to it so that if it is there, you guys don't freak out and you're like, I've seen this before. Remember, C equals lambda nu. Just because those variables look crazy and they look different, like we haven't really seen those in the past, think about it like this. A equals BC. You guys can all solve for an unknown variable there, correct? Okay, we've done that before this year. So just because they look a little bit different doesn't mean anything's going to change. C is the speed of light. That's a constant. It's really like 2.97 or something like that times 10 to the 8th. We're just going to round it to 3. Wavelength, notice it's either meters or nanometers depending on what they give you. And then frequency, which really, guys, frequency is a V kind of waving in the breeze. All right, it's not just a straight up V. It's 1 over seconds or hertz. So you can also write that as 1 seconds to the minus 1. Okay, if you have a negative exponent, it means it's down there as a division on the bottom. Okay, this is an indirect relationship. If one goes up, the other one has to go down. Okay, so let's do an example problem here in just a second. The other type of equation we can see is how energy is related. So we talked about these relationships. Even though, like I said, you're not going to see the equations on your Regents exam, most likely, you still have to understand how energy is related to wavelength or frequency, and how wavelength and frequency are related. So wavelength and frequency, guys, looking at this equation, it's an indirect relationship. When we look at energy and frequency, okay, here's where our constant is. That's called Planck's constant. It's 6.6262 times 10 to the minus 34 joules per, not joules per second, joules times seconds. Okay. If energy goes up, what does frequency have to do here? Since our constant over here in this equation, our constant was on the left side by itself. So if one went up, the other one had to go down. Well, since the constant is here, if energy goes up, what does frequency have to do as well? It goes up as well. So this is a what type of relationship? Direct relationship. Okay? And guys, this should make sense. We talked about it last week. All right? Think about the frequency. Right? If you've got a lot of waves like this in a short time, think about it. When you look and compare these two, all right, this one's got a whole lot of different, a whole lot longer distance to travel than this one does because you've got all these peaks and valleys. If we were to stretch it out, the top line has got a lot longer spot. So they've got to travel and go the same distance, but one has to go up and down a whole lot more, so therefore it has greater energy. Okay? Things like ultraviolet rays, gamma rays. They've got high energy because their frequency is so high. Those are the relationships you've got to be able to identify and look at and understand in your mind, even though we may not have to do any math. All right, so the math may help you, but you won't have to probably do those calculations. All right, get a calculator if you don't have a calculator. We're going to do just a couple, equate one of each. Problem. What is the energy of a quantum of light? What's another term, guys, for quantum of light?
Ray.
Photon. Photon, you got to know that. Okay? And we're going to do a lab next period where you guys are going to get to actually see some photons and kind of analyze them. So it's saying, what is the energy of a quantum? Do you guys have this problem in your packet? All right, so quantum of light at a frequency of this. So what should we do? What's the first thing we need to do here? Every problem, every word problem we have, what should we do? Maybe. Okay, underline or pull out the important pieces. What's one important piece here? The numbers, which is what? What's that number? How would we label that number? It's what? It's the blank of the problem. It says the word right in front of the number. Oh, it's the frequency. Good. All right, so guys, our symbol for frequency is that V. So frequency equals 6.75 times 10 to the 14th, seconds to the minus 1. Remember, we can rewrite that as 1 over seconds. What are we looking for in the problem? That's the other important piece of information. Energy. All right, so that's big E equals question mark. So now with those two pieces of information, we've got to figure out which formula are we going to use. Are we going to use this formula or are we going to use this formula? Should be easy, guys. Which is the one that has energy in it? Yeah, E equals HV. So, do we have H in this problem? No. Why not? Well, it's a constant. So you would be given that if you needed it. Somewhere they would have to give that to you. So we're going to write down, it's Planck's constant. H equals, it's 6.626. 62 times 10 to the minus 34. Joules times seconds. Very, very small number. Okay? So our formula states E equals H nu. This is pretty easy, guys. All we're going to do is just plug and chug. 6.6262 times 10 to the minus 34 joules per second. Now, I ran out of space here, but this is multiplied by our frequency. 6.75 times 10 to the 14th, 1 over second. So seconds is going to cancel out, which means our unit for energy is going to be what? Joules, which is a good unit for energy. All right, that's what we want. So now we have to do the math. Exactly. So when we plug that in, 47 times 10 to the minus 19 joules. All right. Is that math, guys, that complicated? No. It just looks complicated because we haven't seen H or nu before. Okay, but it's still just like A equals BC. If I gave you that all day long, you guys would not have any issues with it. Questions with that problem? All right, here's another one. Okay, let's take a look at this problem. It says a certain yellow light has a wavelength of 575 nanometers. What is the frequency of the light? So, what's our first step we should do? We have a word problem. We need to underline. If you want to underline it, guys, that's fine. You will see me just rewrite my variables out. So I've got wavelength. Wavelength looks like this. It's that lambda. Looks like an upside down Y or like a wishbone. 575 nanometers. Okay, frequency is what I'm looking for. So it's that V waving in the breeze. So I'm going to figure out what formula do I have where it has wavelength and frequency. If I go back and I take a look, yeah, C equals lambda nu. This is the formula that I'm going to use. C equals lambda nu. So C is not given to me in the problem. It's a constant, though, absolutely. So it would be given to you somewhere else to be able to solve this. Our constant is 3 times 10 to the 8th meters per second. Does anybody see a problem that we have? An issue? Yeah, we have nanometers in our wavelength and we have meters in our speed. Okay? So we obviously have to do something, guys. What we're going to do, let's convert that nanometers to meters. Easy way to do that. You, on your reference packets, have the conversion factor for nanometers. Nano is to what? Yeah, 10 to the negative 9. Okay? So, when you multiply this, if we set up a little T-chart, 575 nanometers, we do this, nanometers, 10 to the minus 9 meters. When you do that, guys, 5.75 times 10 to the minus 7 meters. When you're going from nanometers to meters, it will always look like this. Take your number that you have here, put a decimal, and then it's times 10 to the minus 7. It's going to be like that every time with a wavelength that we're looking for light with. Okay? It's simple like that. Or you can do the math. All right, so now we can go ahead and now it's just, again, plug and chug. So we're going to solve for frequency. How do I get frequency by itself? Yeah, divide by wavelength. So we're going to divide by lambda there. So frequency equals C, 3 times 10 to the 8th meters per second, all over 5.75 times 10 to the minus 7 meters. So our frequency, meters are going to cancel out. Oh, our frequency is 1 over seconds. Look at that. What's another unit it could be for 1 over seconds? Seconds to the negative 1. Or what else? There's one other one. Hertz. It could be hertz as well. So any of those units are acceptable because they mean the same thing. Do the math. you're going to have to plug it into the calculator the way that I taught you using the EE function. So go ahead and do that right now. So when you do the math, it's 5.22 times 10 to the 14th, 1 over seconds. Seconds minus 1 or hertz. Folks, any questions with these two equations? Are they that bad? How many people thought they were really complicated when you first saw them? Maybe you did because it's the new symbols, right? But really, as long as you know what the symbols mean, it's not that bad. Okay, I know you guys can do this. All right. So what I have on the board, guys, these are called bright line spectra. Each individual element on the periodic table has its own unique bright line spectrum. Okay? As you can see, the top line that we have here, what do you think this is? What do you think that's the spectrum of? Yeah, that's white light right there. Okay, so this is white light. And then you can see sodium, hydrogen, calcium, magnesium, and neon down below. It is very unique. Each element has its own unique spectra. So the Mars rover, you guys have heard of the Mars rover, right? It's that thing roving around Mars, right? I'll see what I did there. This is exactly how it identifies what elements are on the surface of Mars. All right, it shoots some energy at the different particles, and then it can analyze the spectrum when it reads it and it comes back to it. You're going to do this next period. We're going to make it dark in here, but we'll worry about that in between classes. Each one of these is unique to each different element. Some have more lines, some have less. Okay. What's happening, though, to see these lines? We talked about it last week. What happens for you to see color? Like with fireworks. Anybody remember? Yeah. So the electrons will get excited. They go up to the excited state, and then they are released, and they come back down to the what state? The ground state, the lower energy level. When do you see the light, though? Is it when the electrons jump up or when they come back down? Yeah, it's when they come back down. So these elements, guys, when we see these spectrums here, all right, it's when those electrons in one of the energy levels, they jump up and they come back down. When they come back down, they release that energy they absorbed that allowed them to jump up higher, and that's what we see here, all right, is these lines. How this applies to us, okay, how this applies to us is we're going to be given something like this. So this is an old Regents exam question. All right, so this is the type of thing you're going to see. It says, given the bright line spectra of 3 elements, in the spectrum of a mixture formed, at least 2 of these elements, okay, so the mixture has at least 2 of them, gives you the wavelengths. It says, which elements are present in this mixture? How do you think we go about solving this problem? Garrett? Yeah, exactly. You're going to go to that mixture, and you just kind of go up to the lines that they see. If you don't see that line on there, it doesn't mean it's there. It means it's not there. So which element, guys, what ones here in this problem are present in the mixture? So just go up. Okay, I see this one, so that one's going to be there. I see this one's right there. This one's here. Just kind of draw lines up to see which ones, and as where they match up, that's what you want to see. So which one is not in this mixture? G. Element G, guys, is not in the mixture. So now you got to go through and be careful as you're reading through here. Okay? You pick the right one. So anywhere you see G, you can mark off, which would be choice 1 would be your correct answer here. This is how you're going to have to apply these spectrum in June on your Regents exam. So I want you guys to go through the next 3 and try it on your own. Second example that you guys had, we have our mixture. Which element is not present in the mixture? Are they? You sure? Cadmium, guys, look. It's got 2 right there, and it's not there. So, where?
Yeah, but it's not right there in the mixture.
In the mixture? Here's the thing. All the lines have to be present in the mixture, guys, because remember, they are unique to every individual element. Because if you line it up, this one's not in the mixture, even though this one is. This one's not in the mixture. This one's not. So there are maybe two that are in the mixture, but it's got to be all or nothing, which is why I'm glad I put this one on there. It's all or nothing, okay? So keep that in mind as you're looking at it, because it's unique to every element. What about this one that says gas A, B, C, and D, and then you have an unknown mixture? Which element or elements are not in the mixture?
Gas B and C.
Yeah, B and C, guys, they are not in the mixture. Again, you've got a double line here that's not there, and you've got a double line there that's not there as well. Okay? Questions? I think you guys had one more on yours. I don't have a slide of it up here. All right. So when you don't have one more? Yeah. So which one is it on that last one?
Element A.
Element A should be the last one. At the top. It's okay if you didn't. Guys, you'll have a few questions like this. You'll see that on your test. Hopefully they are easier questions for you. All right, get your Unit 1 packets back out. Unit 1 packets. We're going to go back and talk about classifying matter again. Guys, this should be a review. You have a lot of notes hopefully written down about this stuff. It's the very last page, page 12 of your Unit 1 packet. So physical properties, who can kind of tell me what a physical property is?
Being tall.
Look at your notes. Tall, so that would be an example of one. But what does it mean? What's our definition of a physical property?
A property that can be measured.
Yeah, measured how? Or? Seen, observed, absolutely. Like it says right up here. All right, without changing the identity. So a physical property is observed or measured. A physical change doesn't change the identity. So something like grinding or cutting or melting or boiling. Okay. What we're going to have to be able to do, guys, is you're going to be able to have to classify matter, types of changes. Okay. Chemical property is the ability of a substance to undergo or transform it from one thing to another. So like charcoal or wood burning is an example. So something like flammability or combustibility or reactivity level, that is a chemical property. And then the change is where you get a brand new substance. Okay, it's in a different one. So you have reactants and products. You can't get it back to its original state. That's kind of the way I think about it. All right. So we talked about the 4 signs. Make sure you know these 4 signs of a chemical change. Remember, odor is only sometimes, so we're not going to really worry about that too much. But you've got to know a change in temperature. So heat gained or lost. Formation of a gas. How do you know if a gas forms? What do you see? Bubbles. Okay. Formation of precipitate. It's a solid from 2 different solutions. And then a color changes sometimes. All right. Exothermic feels what? Hot. Why? Because what's happening? It's releasing or emitting energy. Endothermic feels cold to the touch. Okay, we've talked about that. Endothermic is absorbing. It's taking energy out of a system. All right, so we talked about the states of matter, correct? We defined those. We're going to skip through that. We started talking about atom, element, compound, correct? Okay, we've already gone over that. This piece. Have we gone through all this chart? Okay. So I'm going to give